The moment of momentum change theorem of mechanical system, article 10.9 of the book, Mechanical Systems Calculations of the Marine Facilities. We will consider the exercise, but first a little bit about the concept of the momentum change theorem. We did consider in the articles 10.7, 10.8 theorems of the momentum change theorems for the material point motion. This is a kinematic characteristic of the motion of the material point or material body in article 10.8. We considered the motion of the mechanical body consisting of the discrete concentrated loads of the material points. So this was for the translational motion of the mechanical body. If we can sometime to consider the complex motion, consisting of the rotating motion and maybe the translational motion together of the mechanical system, we can sometimes reuse this to the translational motion. So we can, if for example the mechanical system rotates, this could be as a translational motion by the circular trajectories of the separate elements of the mechanical system, and we can do the consideration of that. But as well, we have the concept of the momentum as well is the kinematic characteristic of the motion of the massive bodies of the mechanical system consisting of the separate elements, or maybe of the continuous bodies motion with the rotation. So the characteristic which is generally proportional to the characteristic of inertia of the mechanical system for the rotation, that is the moment of inertia of the mechanical system, or consisting of the separate parts of the continuous body, moment of inertia. And when it multiplied by the angular velocity of the rotation, this will be the moment of momentum, as just momentum is a product of the mass of the element or the point of the mechanical system by the velocity of the motion, or center mass, or just center mass of the element, or center mass of the mechanical system. So the momentum, definitely one case is the product of the moment of inertia onto the angular velocity. This as well is of the use when we consider the rotational motion or the just angular motion of the bodies. For example, for the differential equations, this is widely used, etc. And as well, we have the momentum change theorem, or momentum, as you can say, the moment of the amount of the motion. Moment of amount of the motion, the moment of a momentum, or we can say the moment of the kinetic moment. The kinetic moment too is this moment of momentum, is kinetic moment, or moment of the amount of the motion. And we have to remember that this is very proportional to the characteristic of the inertia of the rotation of the mechanical system at element or the continuous bodies, and the proportional to angular velocities of this rotation. This can be as well considered in the projection of the axis, because we know for sure that the moments are the characteristic of vector characteristic. So we can do that as well. Okay, but let's consider the lesson. The lesson we have to the exercise, the rectangular platform. This is a rectangular platform, this one. The size of platform is the length, two R's, R and R is center of the mass of this mechanical platform, center of gravity mechanical platform, and the width of mechanical platform. This is rectangular, obviously this is symmetric shape of the platform. The width is R divided by 2 is just a half, and the next one R divided by 2. This is mechanical platform. We have the initial angular velocity of rotation relative to the vertical axis. We have see the here 0 is a vertical axis. Just from the point of view, we look to the direction of the plane of the draw 10, 9, 1p. Here we have in the isometry, we can see that this axis vertical and platform is horizontal, rotating around the point 0 relative to the axis, not the point, but relative to the axis, with angular velocity omega 0. On the platform, we have the channel key A, the straight channel on the right side of the platform with the load located here, load D. It moves, and the mass of the platform is 30 kilos, and the mass of this load D is 6 kilos, and the size of the platform r and r is each r is 1 meter, and we have an initial velocity 4 radian per second. Radians equal, just we can denote like seconds minus 1 power minus 1, angular velocity 0, initial angular velocity. And we have the pattern of the motion of the load by the channel. This is a stretch motion of the load, and the pattern is 0.6 multiplied by t. The motion d, the motion of the mass 6 kilos. And as well, we have the external moment. We assume that it is a couple of forces with the resultant rotating moment. Rotating moment is 12 by t squared, Newton by meter. This is assigned. And the issue is what is the dependence of the angular velocity of the rotation of the platform in dependence on time. So we have two dependencies on time of the location of the load, and we have the magnitude of the moment rotating this platform. This is flat motion. We could consider this moment as the scalar magnitude and the flat motion of the platform with all forces and all the points, etc., acting here moves parallel to the definite horizontal plane. So no the forces of the weight of the platform or the weight of the load directly act on the magnitude of the momentum of the motion of this platform or on the momentum. So this is flat motion of the platform. I mean the horizontal rotation with the moved on the horizontal rotation and the action of the external moment m, and with a definite load which moves by the channel here, by the straight channel on the right side of this platform. So okay, let's consider the decision of this definite one issue. The load begins to move along the chute here, the horizontal channel, yes, straight channel, in accordance with the pattern. The same, this is just a little bit more about the data, initial data assigned. At the same time, a pair of external forces begin to act at the platform, initiating the moment 12 by t squared. The exercise assigns to 1 to determine the pattern of the angular velocity of the platform plus dependence on time, functional dependence on time of the angular velocity in accordance with the momentum change theorem. The momentum, or kinetic momentum, we can say the kinetic moment of mechanical system in the projections onto z-axis equal has the form. This is momentum derivative. In projection on the applied axis, we consider only the applied axis because this is a flat motion. The applied axis is in the perpendicular to the plane of this draw, equal to the total of the external moment of the external forces. We have the couple of certain forces. Assume that the two external forces couple cause the external moment. So equal to this, only one. The dimension external moment detection leads to change of the kinetic moment or moment of the momentum. The dimension of the momentum in the international system of units, system of international units, so this in French language you can see, kilos by meter squared divided by second, or Newton multiplied by meter multiplied by second, or just joule is unit of the energy multiplied by second, etc. When the platform is exposed to moment of external forces, 12 by t squared, a time-dependent moment of momentum corresponding the time integrating of the moment of the external power forces is so this derivative equal to the moment of the impulse of this definite one moment caused during the definite time t. And then we can find that after the integration of this equation, we can find that the magnitude of the momentum or kinetic moment equals to 4 by t power to 3 plus c1. c1 is a definite constant of the integration. It's subject of our next definition. The momentum of the external force corresponding to the rotating platform with this load moving by the channel So it consists of two summands. This is moment of momentum, kinetic moment of the rotation of around the applied axis of the platform one with the definite mass assigned, and this is the momentum of the motion, or the momentum of the rotating, the complex motion with the rotating of the load moving by the channel with the assigned partner of the motion. The moment of which is the kinetic moment is equal moment of inertia multiplied by the angular velocity as just a momentum equal to mass multiplied by the translational velocity. The moment of momentum is equal to moment of inertia multiplied by angular velocity. Okay, so we have to find the moment of inertia first of the platform, because we have to find these two summands. So the moment of momentum or kinetic moment of this mechanical system. Moment of inertia equals, according to the Huygens-Steiner theorem, of two summands for this definite one platform. Because we have the axis of the rotation, which not coincides with the center of the mass of this platform. Then we will have a total of two summands. The first summand is the moment of inertia of the rectangular platform around the point of location of center of mass, and the second summand is the mass of the platform multiplied by squared radius between the axis of the rotation and the center of the mass of the platform. This is together transfer, the second sum transfer moment of inertia. So after the substitute the known formulas, we got in one of the previous articles, not remember which one definitely, that what is the moment of inertia of the plate, for example. But just let me remind that equal to mass of the plate divided by 12, plate of the homogeneous distribution of the mass by the plate, multiplied by the sizes squared of this plate. The first size is 2r and second size is r, so we can just multiply it, and as well we can consider the transfer moment of inertia, the distance, that is the radius between the axis of rotation of the platform and the point of the center of the mass of the platform. The size is r. Why r? Because we can see here this is the center of the this is the center of the mass of the platform, is shown here on all forces action, or parallel to the axis of rotation, or intersects as the reactions of the support the axis of rotation. That is, they do not cause the action of the external moment onto the moment of momentum due to the momentum change theorem. This is just remark. But let me remind you that the location of the center of the mass of this rectangular platform is by the radius r from the axis of rotation of this platform. So let's return back and to do the this distance r. So after the all transformations here, we can find that the moment of inertia of the rectangular platform is 17/12 multiplied by mass of the platform multiplied by the squared size r. Size r, we let's remind, is a wide platform and just a half of the length of the platform. And the momentum, if we have this definition of the moment of inertia of the platform, the momentum of the platform rotating is equal by the product of this moment of inertia by the angular velocity. We can do that all, and we can substitute the data. We know assigned as the mass of platform and the size r, so 1 meter, let me remind. And after the all substitute, we can find that momentum of the platform equals 242.5 multiplied by the omega angular velocity of rotation of the platform, kilograms by square meter divided by second. The momentum of the load. Next question, because we have two elements of mechanical system. The first is the platform. The second one is the load. Momentum load L to relative the axis of rotation consists of two parts, because the load participates in the two motions. The first is a relative motion relative to the platform. This with the velocity v2. This is 2. This is for the load. The first we have for the platform. Second is the load v2r. The relative motion of the load relative to the platform. This is assigned as a dependence on time and multiplied by OA. OA is the radius between the point of rotation and the line of direction of the motion of the load 2, and the second one is motion or the transfer motion with the platform. Transfer motion the same as m2, yes, because we are talking about the momentum, and multiplied by the velocity of the transfer motion, multiplied by the radius from axis of the rotation by the point of location of the instantaneous location of the load, instantaneous location. This is the characteristic, the instantaneous. Depend on time. So let me show you on the picture here. So we have this transfer velocity, this when the load moves together with the rotating platform. This velocity depends on the definite one-point radius. So first, this radius from 0 point, this is axis point of with intersection with the platform, to the point location of the load, instantaneous point of the location of the load. This velocity by the perpendicular directed by the tangent of the circle of the around this when rotating the platform around the axis applied, and the magnitude of this velocity equals to angular velocity multiplied by the radius 0 and the d. And the d we can find as we have assigned dependence of the motion of the load along the channel. We have s as a motion, 0.6 multiplied by t, as I remember about it, assigned the magnitude of the coordinate s of the relative motion of the load by the platform. So we have right angle triangle, so we can find the radius as one side is 1.5 r from and the channel is in the middle of the second part of the platform. So the r is just half of the platform. So the one leg is 1.5 r, another one leg is s, and we can find the radius OD as a squared. Actually, OD is a square root of 2 squared summands of 1.5 r squared and s squared. But to have the momentum in the formula, we definitely need to have the squared radius squared. So we don't need to take the square root when finding the size 0d. We have to use the final decision about the squared magnitude of the radius 0d. This is for the rotation or transfer rotation of this the load together with the platform, with this one, the transfer rotation. This is relative velocity, because we have assigned the motion of the load along this channel. So this velocity direction is usually by the channel perpendicular the shortest the radius, that is the shortest distance between the axis of rotation to the line of the motion of this load is just only 1.5 by r. And we have other directions. You can see that these two velocities of the transfer motion of this load and the velocity of the relative motion do not coincide by the direction. They incline for definite one angle, so we have here. Okay, let's return back. The momentum equals one hand of the product of the mass by the velocity of relative motion and the distance between the short distance between the axis of the rotation of the platform and the axis of the channel, or 0a. And the second summand is the momentum or kinetic moment of the rotation. The point when it moves together, when it moves together with the platform, and this is dependent on the squared 0d or OD by the velocity. Why? Because the translational velocity itself is equal to 0d or velocity. So we have 0d squared. This is this factor comes from the concept of the momentum or kinetic moment. And the second one, because we have finally the squared degree of 0d, the degree, so the second one 0d as a factor here, and this second sum. And this second comes from the definition of the translational velocity of the transfer motion as a product of 0d as well by the angular velocity. So we have angular velocity here on the first degree and 0d squared, and this 0d is square root of 1.5 r says one leg and plus squared, and plus the s as a coordinate of the location of the relative location, instantaneous coordinate of relative location of the load in the channel assigned by the pattern of the motion of the load assigned. This we can have the relative motion characteristic. And the first one summoned relative motion equal as well by the squared 0.82. Okay, if we will introduce the angular velocity as a concept of the angular velocity, the relative angular velocity, so we have two angular velocities of the rotation of the load in the transfer motion here. That's the angular velocity of rotation platform, and the relative angular velocity relative to the platform is then we can substitute as one of translational velocities of relative motion. We can find as a product of the radius by the relative angular velocity of the rotation. Within concept of the rotation of this load. Okay. Next, we can substitute all data we have into the last one dependence, this one dependence here. The angular velocity, because it's first derivative by time of the assigned pattern of the motion of the load by the channel. The pattern was 0.6 multiplied by t. This was the initial data. So as we know that the translational velocity equal to the first derivative of the wave, first derivative of the distance. So the first derivative when 0.6 by t, first derivative is 0.6 meter per second, and we have OA equal to 1.5. It's the shortest distance between the axis of rotation of the platform to the axis of the channel. This is 1.5 meter, due to the r is 1 meter, and OD is equal OA plus AD squared. So we have one leg is 1.5 squared. We need squared OD. And the second, the same size as 0.6 by time assigned magnitude of the S, the second one, leg squared. So we consider two legs. The fourth leg, 1.5 R is 1 meter, and the second leg S assigned 0.6 multiplied by T. Okay, we did substitute the tau. And after that, we do definite, we had substitute on the definition as a total of this in the definition of the momentum, kinetic moment of the load when rotating in the complex motion relative to the applied axis Z. And we can find the momentum of the load D motion together. After the simplification, this is 5.4 plus 13.5 in the brackets plus 2.16 multiplied by t squared, and this all multiplied by the omega angular velocity of rotation of the because we have here moment and here omega of the rotation of the platform, because the second summand comes from the transfer motion of the point. We have two in complex motion. We have relative motion relative to the coordinate system associated in a definite one case with the rotating motion of the plate, and with the transfer motion and relative motion of the point relative to the plate. Use the momentum or kinetic moment change theorem of the mechanical system, equating the momentum of the system, the platform, and the load, and momentum from the impact of the pair of forces. We have assigned pair of forces. We have assigned pair of forces here, 12 plus t, 12 by t squared. Momentum of forces. We did have the transform as 12 by t squared, having the decision of this differential equation. We in the differential form, this 12 by t squared we assigned, and in the integral form we have just on the momentum equal to 4 by t power to 3 plus c1. We did have this originally, and we can next do the definite mathematical transformation that we will have the general dependence with the constant c1. Constant comes from the integration of the theorem of the momentum change. When we transform this theorem from the differential to the integral form. To find the angular velocity, the platform, we have to find this constant c. We substitute here, instead of velocity assigned initial velocity, we have initial angular velocity 4 radians per second. This is assigned originally. And we have substituted this for time equal to 0. Instead of t, we can substitute 0, only c1 we have, and c we have together within two summands. 56 by 4, and this 56 by 4. Initial angular velocity plus 5.4, this is 0. When t0, this is 0, equal to c1. And when we next this total 56 by 4 plus substitute here back, we can just reduce the same summands on the right and the left sides. Phi 5.4 on the left and 5.4 from the right when we substitute it into the equation. And we will have the final equation with only variables angular velocity subject to find, and the time. After the simple transform, we can find the angular velocity of rotation of the platform and the action of the having the initial angular velocity and the action of the couple of forces which caused the rotation moment assigned with in the pattern by the definite partner of the assignment, and having the channel with the load moving by the pattern of the coordinate of the location of the load as well assigned. We will have appropriately complex, relatively complex dependence of the angular velocity equal to the ratio in the numerator we have 4 multiplied by t power to 3 plus 224 and divided by the denominator 2.16 multiplied by t squared plus 56 radian per second. That's what we have to find due to the assignment of the motion of this platform with the load and action of the external mole. This is flat motion, and the all data we had here assigned the moment dependence on time and the coordinate s or location of the load dependence on time as well. The masses we have, the sizes of the platform. This all we have, and the masses of the platform and the load, etc. Questions and comments. 10.9.1, the equality of the change during certain time of the momentum, that is kinetic moment, in other words, during rotation of a mechanical system and the moment of external forces acting during this time, the momentum of the resultant external forces in accordance with the momentum change theory. Yeah, the action of the external moment equal during the definite time equal to the change of the momentum or kinetic moment when the massive elements of the mechanical system moves with definite angular velocities. We can find the momentum or kinetic moment. 10.9.2, finding the momentum of external forces by time integration of the moments of the external forces of the moment of the resultant external force. We can just having the momentum change theorem. On the left we have the derivative of momentum is a product of the characteristic of the rotational inertia of the elements mechanical system on the angular velocity of the rotation. This derivative by time equal to the increment of this momentum or kinetic moment to the increment of time. On the right we have the total of the external moments acting on the mechanical system, but we can just subdivide the variables, and we can remove the denominator from the left side of the momentum change theorem to the right side as a factor, and we will have the differential equation, and we can next integrate this equation and find the integral form of the momentum change theorem with definite constant of the integration. If we have initial conditions, we can find the constant and use this for decision of the issues. The next 10.9.3, determination of the moment of inertia of mass during rotation of an element of mechanical system as a sum of its own moment of inertia related to the center of gravity and system of the system element, and the transferring moment of inertia as a product of the mass of the element by the square of the distance from the axis of rotation to the center of the gravity of this element. We say, yeah, that is the center to the center of the mass. the distance squared is a transfer moment of inertia. This is Huygens-Steiner theorem, how to find the moment of inertia rotation relative to the arbitrary axis, because we have the own moment of inertia when rotating the massive element mechanical system relative to the axis passing by its center of the mass, center of the gravity. But if the axis do not crosses by the center, so we will have the own moment of inertia, the transfer as a summons to find the total moment of inertia of the mechanical system or mechanical body, or maybe solid body, maybe continuous body, or the system consisting of the discrete elements, discrete concentrated loads, etc. 10.9 for determination of the moment of momentum of an element of a mechanical system as a product of the moment of inertia of the mass relative to the axis of its rotation and the angular velocity of rotation. Yes, this definition of the moment of momentum or kinetic moment or the moment of the amount of the motion of the element mechanical system. This, to find that, we have to find the characteristic of rotational inertia, like moment of the inertia of the element mechanical system, and multiply this onto the angular velocity. This will be the vector magnitude. We can find as well the components and projections on the axis of the coordinates, and to find the elements, the components, projections of this vector of the momentum in the next. 10.9.5 determination of the moment of momentum of an element of mechanical system during its complex motion as a sum of the moment of its own motion related to the rotating coordinate system and the moment of the transferring motion of the rotating coordinate system relative to the axis of rotation. Exactly. So if we have the complex motion, so we have elements mechanical system which moves relatively another elements or relatively the general mechanical system, we will consider first, we have to consider two motions. First is the transfer motion, that is the motion and rotation. I mean, because we are talking about the moment of momentum, or kinetic moment, or the massive motion. So then we have to find the first the momentum appropriate to the motion together with motion of definite one element together with the transfer motion of the system within which this element is defined. And the second is a motion of this element relative to this system coordinate, moved coordinate system. For the complex motion, we have to consider two rotations. One rotation of the system of coordinate relative to the fixed one. And the second is rotation of the element within the moving coordinate system to find the kinetic moment of moment of the momentum. 10.9.6, the intrinsic moment of momentum is equal to the product of the moment of inertia of an element of the mechanical system relative to stationary coordinate system, assuming that the center of gravity of the system element is located in a moving coordinate system rotating relative to the stationary one with the angular velocity of rotation of a moving coordinate system. Intrinsic moment, or the moment of the momentum, corresponds to the own characteristics of inertia of an element mechanical system related to the stationary coordinate system. So we have to consider for the if the axis of rotation not passes through the center of the mass of the mechanical system, we have to consider first the inertial characteristic of the rotation relative of the system relative to its main mechanical systems center of mass, and the rotation of the center of mass mechanical system relative to the axis of rotation assigned. Thank you.